We are taught that light is the fastest thing in existence, instantly illuminating the dark. But when you look at the sheer scale of the universe, light is actually agonizingly slow. It takes 4 years just to reach the nearest star. To cross our own galaxy, it takes 100,000 years. This reveals a sobering reality. The speed limit of the cosmos acts as a vast, silent boundary that keeps star systems isolated from one another. This implies that humanity might be confined to this solar system for ages, gazing at cosmic oceans we can seemingly never cross. We're about to explore the true, mind-bending scale of deep space, why the universe seems built to keep worlds apart, and the theoretical ways, like warp drives and wormholes, that we might one day bridge the vastness and reach the stars. If you want to understand the true size of our reality, hit that like button and subscribe, and tell me in the comments, do you think humans will ever live on another star system? Now settle in, relax. We begin. Light moves at 299,792,458 meters per second. This number is carved into the structure of reality. It governs not just light, but gravity, time, and the relationship between energy and matter. Nothing with mass can reach it. The closer you push toward light speed, the more energy you need, escalating exponentially until you would require infinite power to cross the final threshold. Physics does not merely discourage faster than light travel, it forbids it with mathematical certainty. And yet, this speed that feels so absolute, so untouchable, is cosmically glacial. A photon leaving the Sun takes 8 minutes to reach Earth. It sounds fast until you scale up. That same photon needs 5.5 hours to reach Pluto, nearly a full working day to cross a solar system that is, by galactic standards, a grain of sand. The Oort Cloud, the icy shell at the true edge of our solar system, sits so far out that light takes nearly 2 years to traverse it. Proxima Centauri is the closest star to us after the Sun, a faint red dwarf barely visible even with telescopes. It lies 4.24 light-years away, meaning light itself, travelling without pause, without obstacle, takes 4 years and 3 months to make the crossing. If we sent a message today and an alien civilization there replied instantly, we would wait 8.5 years for the answer. One human conversation across the void would outlast most careers. This silence is deafening. The universe operates on deep time, where human lifetimes are just fleeting sparks in the dark. Light speed reveals a humbling truth. The cosmos is not just vast, it is effectively infinite compared to our tiny, fragile existence. 12 stars sit within 10 light-years of Earth, a handful of cosmic neighbours in an otherwise empty desert. The nearest potentially habitable world orbits Proxima Centauri itself, locked in a tight orbit around that dim red star. Even if that planet holds oceans, atmosphere and life, reaching it at light speed requires more than 4 years of continuous travel. And light speed, as we have established, is impossible for anything with mass. We have built machines like Voyager 1, hurling them into the abyss at 17 kilometers per second. It feels fast to us. But to the galaxy, Voyager is standing still. At its current speed, it would take 73,000 years just to reach our nearest neighbour, longer than recorded human history. Even our boldest concepts, like laser sails pushing probes to 20% of light speed, would still mean waiting decades for a single image to return, and that is just for the nearest star. There are 400 billion others waiting in the dark. The question looms larger with every passing discovery. Thousands of exoplanets now fill our catalogues, many orbiting in habitable zones where liquid water could exist. Some circle nearby stars, others lie dozens, hundreds, thousands of light-years distant. We see them. We measure their size, their temperature, the composition of their atmospheres. We detect the fingerprints of water vapour, methane, oxygen, and we cannot reach them. Not in a human lifetime, not in 100 human lifetimes, not even at the speed of light. So we turn to alternatives, to ideas that sound like science fiction but emerge from legitimate physics. Warp drives, first proposed theoretically, that compress space in front of a ship and expand it behind, moving the bubble of space itself rather than the ship through space. If space moves, the ship inside remains stationary relative to its local bubble, sidestepping the light speed restriction entirely. The Alcubierre drive, named after the physicist who formalised the mathematics, suggests this might be possible. but it requires exotic matter with negative energy density, something we have never observed and may not exist. Wormholes offer another theoretical escape. Einstein's equations allow for tunnels through space-time, shortcuts connecting distant regions of the universe. Fall into one end, emerge light years away, bypassing the vast gulfs between stars entirely. But wormholes, if they exist at all, would require immense energy to stabilize, and we have no idea how to create or control one. They remain mathematical curiosities, beautiful on paper, unreachable in practice. Then there are the slower, more pragmatic visions. Generation ships, vast vessels carrying thousands of people across the void, each generation living and dying aboard while the ship crawls toward a distant star over centuries. Suspended animation, or cryogenic sleep, freezing human bodies to pause biological aging during decades-long voyages. Digital consciousness transfer, uploading human minds into machines that do not age, do not hunger, do not despair at the emptiness. Each idea trades speed for endurance, accepting the vast timescales the universe imposes and finding ways to survive them. But none of these erase the fundamental problem. Light speed is too slow, and we are bound by it. Imagine standing in the quiet dark, looking up, knowing that the closest star beyond our sun is not a gentle stroll away. It is Proxima Centauri, a cold ember glowing just barely at the edge of visibility. In cosmic terms, it is our next-door neighbour, 4.2 light-years from home. But those light years are not just a number. They are a desert, dry and hostile, stretching wider than any ocean on Earth can pretend to match. Light, in all its speed, needs more than 4 years to bridge this gap. 4 years, moving relentlessly, never stopping to rest, never diverted by obstacle or delay. Only then does it touch Proxima's lonely pale planet. The reality stings more when you imagine sending a message there and waiting 4 years for the first flicker of acknowledgement, 8 for a single exchange. Human patience, human lifetimes, are nothing to this river of time. Now what does it mean for us, beings who dream of crossing these gulfs? The fastest spacecraft ever created, NASA's Parker Solar Probe, races toward the Sun at over 190 kilometers per second, more than 690,000 kilometers per hour. Even at that nearly unthinkable velocity, it achieves just a tiny fraction of light speed, less than 1/10%. If we could send Parker Solar Probe in a straight line to Proxima Centauri, it would take more than 6,000 years to make the crossing. Every human civilization would rise and fall during its journey. Voyager 1, the silent envoy now drifting far beyond Pluto, moves much slower, 17 kilometers per second. If sent towards Proxima Centauri, it would need more than 70,000 years. That is the distance between us and the next chapter of the cosmos. The numbers become more haunting the closer you look. In recent years, astronomers have found a rocky world orbiting in Proxima's slim zone of warmth, a place that could, with extraordinary luck, host water, wind, perhaps even life. It is so tantalizingly close, so heartbreakingly out of reach. If we could find a way, any way, to travel as fast as light, a round trip would still mean 8 years spent between arrivals, between questions and replies, between hope and the next heartbeat of discovery. And yet, as hard as the universe slams shut one door, human curiosity begins to probe at the hinges. What if speed is not the only answer? What if, instead of outpacing light, we learn how to wait, sending generations of explorers or turning to physics for a loophole no one has yet imagined? The stars will wait. The river of darkness between us and Proxima Centauri flows slow, but it gives us the gift of longing, of imagination, seeking a way across. The universe's nearest outpost is more distant than our oldest myth, but the dream of reaching out, of touching another sun, remains. It fuels every question born under the night sky and propels us even now to wonder, what if we found a way? Proxima Centauri is not alone in its vigil. A dozen stars sit within 10 light-years of Earth, scattered across the black like distant campfires. They are the nearest members of the vast stellar community, the ones we once dreamed might be within our grasp. But light, even light itself, requires 6 to 12 years to reach most of them. And we are not light. We are flesh, metal, ambition bound by gravity and physics. The fastest object humanity has ever built is NASA's Parker Solar Probe. which screamed past the Sun on Christmas Eve 2024 at 192 kilometers per second. It set a record that still stands, reaching 692,000 kilometers per hour as it dove closer to our star than any machine in history. This is not a gentle drift through space. This is velocity so extreme that the probe experiences temperatures near 2,500 degrees Fahrenheit, protected only by a heat shield engineered to endure conditions no material should survive. And yet, for all its speed, Parker's solar probe moves at just 0.06% of light speed. If we could somehow redirect it toward the nearest stars, it would take thousands of years to reach even the closest ones. Proxima Centauri would demand over 6,000 years. The next star, Barnard's star at 6 light-years, would take 9,000. Sirius, the brightest star in our night sky sitting 8.5 light-years away, would require over 13,000 years of travel. Helios 2, the previous record holder for speed, reached 70 kilometers per second in 1976 and held that title for nearly 50 years. Voyager 1, launched in 1977, moves at 17 kilometers per second and is now so far from home that its radio signals take over 22 hours to reach Earth. It is the most distant human-made object, drifting in interstellar space beyond the influence of the Sun. But even Voyager, even after decades of uninterrupted flight, has barely begun to scratch the surface of the void. It would take 73,000 years to reach Proxima Centauri if it were headed that way, which it is not. This is the trap of the local neighbourhood. These stars are close by cosmic measure, they are neighbours, and they remain impossibly distant. We see them with our eyes, chart their orbits, measure their luminosity. Some have planets, some might have worlds with water, atmosphere, the ingredients for life. And none of it matters, because the gap between us and them is measured not in distance alone, but in generations, in civilizations. Engineers dream of solutions. Light sails pushed by ground-based lasers could, in theory, accelerate small probes to 20% of light speed. 20 years to Proxima Centauri. A single human lifetime to reach the nearest star. But these are not crude vessels. They are gram-scale wafers, tiny machines carrying sensors and transmitters, racing through the dark with no way to slow down, no way to stop. They would scream past their targets at relativistic speed, gathering data for mere minutes before vanishing into the endless black beyond. And even this remains theoretical. The engineering challenges are immense. A ground-based laser array powerful enough to accelerate such probes requires gigawatts of energy and kilometers of infrastructure. The sails must survive intense laser bombardment without warping or tearing. The payloads must endure accelerations measured in thousands of times Earth gravity. And after all of that, after decades of travel across the void, the probes must transmit their findings back across light-years of space, with power sources no larger than a coin. The local neighbourhood is a test, a reminder that proximity in space means nothing without the ability to cross it. 12 stars within 10 light-years, dozens more within 20, hundreds within 50, and every single one of them sits beyond the horizon of human reach, waiting in silence for a species that dreams of flight but remains shackled to the ground. Before we dream of stars, we must first confront the boundary of our own backyard. The solar system does not end at Pluto. It stretches far beyond the planets, beyond the icy worlds of the Kuiper Belt, into a vast shell of frozen debris called the Oort Cloud. This is the true edge, a region so remote that light itself takes nearly 2 years to cross from one side to the other. 2 years, not to reach another star, not to visit another galaxy. Just to traverse the outermost boundary of the space we call home. The Oort Cloud is a gravitational graveyard, a trillion icy fragments left over from the birth of the solar system, drifting in darkness 5,000 to 100,000 times farther from the Sun than Earth. Comets that plunge toward the inner solar system, blazing across our skies with their brilliant tails, originate here. They fall inward after being nudged by passing stars or the gentle tug of the galaxy itself, spending thousands of years on their journey before we see them for a brief moment. At light speed, you could leave Earth and reach the Moon in 1.3 seconds. Mars, depending on its position in orbit, would take between 3 and 22 minutes. Jupiter sits 43 minutes away when closest. Neptune, the outermost planet, demands over 4 hours, but the Oort Cloud, nearly 2 years of continuous travel at the ultimate cosmic speed limit. Now scale this to human technology. Parker Solar Probe, the fastest object humanity has ever built, achieved 192 kilometers per second in December 2024. This is 0.6% of light speed. At that velocity, crossing the Oort Cloud would take over 300 years. 3 centuries just to leave our solar system, to finally step beyond the Sun's gravitational dominion and enter true interstellar space. Voyager 1 crossed into interstellar space in August 2012, becoming the first human-made object to leave the heliosphere, the bubble of charged particles blown outward by the solar wind. It took 35 years of continuous flight to reach that milestone, travelling at 17 kilometers per second. But Voyager 1 has not left the solar system, not truly. It remains within the gravitational influence of the Sun, still bound to our star by invisible threads. It will take another 30,000 years before Voyager exits the Oort Cloud entirely and becomes a wanderer among the stars. This is the scale we're dealing with. Our solar system is not a compact cluster of planets circling a star. It is a vast domain stretching trillions of kilometers into the void, and even light finds it slow going. The distance from the Sun to Proxima Centauri is 268,000 times the distance from the Sun to Earth. Written another way, if Earth's orbit around the Sun were the size of a coin, Proxima Centauri would sit 4 kilometers away, and the Oort Cloud would barely extend beyond the edge of that coin. We speak of interstellar travel as if the gap between stars is the only obstacle, but we cannot even leave our own star's reach in a human lifetime using our fastest machines. The solar system is not a launch pad. It is a prison yard, and the walls stretch farther than most can imagine. Before we worry about the 4 years to Proxima Centauri, we must reckon with the 2 years just to clear our own doorstep, at light speed, a velocity we cannot hope to achieve. And this raises the deeper question. If even leaving home takes lifetimes, what hope do we have of crossing the oceans beyond? The answer may not lie in speed alone. Perhaps we must think differently. Generation ships that carry entire societies across the void, digital consciousness uploaded into machines that do not age, or technologies that sidestep the rules entirely, warp drives that fold space, wormholes that punch through reality. The universe has built walls, but humanity has never stopped searching for doors. Proxima Centauri does not stand alone. It orbits as part of a triple star system called Alpha Centauri, the brightest stellar system in the southern sky and the closest to our Sun. The other 2 members, Alpha Centauri A and Alpha Centauri B, form a binary pair locked in a gravitational waltz, circling each other every 80 years. Proxima, the faint red companion, drifts at the outer edge of the system, bound loosely to the brighter pair by gravity's invisible thread. This is humanity's nearest stellar neighbour. 3 suns instead of 1, orbited by at least 1 rocky world and possibly others. Alpha Centauri A resembles our own Sun, slightly larger and brighter. Alpha Centauri B burns dimmer and cooler, and Proxima, the closest of all at 4.24 light-years, is a red dwarf barely 1/7 the diameter of the Sun, glowing faintly in the infrared. If there were ever a natural target for humanity's first interstellar mission, this would be it. 3 stars for the price of 1 journey, potentially habitable worlds, a cosmic oasis just beyond our doorstep, and yet, the distance remains insurmountable. 4.24 years at light speed, over 6,000 years using the fastest spacecraft ever built, more than 70,000 years aboard Voyager 1. The problem is not just distance, it is energy. Accelerating even a small probe to a meaningful fraction of light speed requires power that dwarfs anything humanity has achieved. Chemical rockets, the workhorses that lifted Apollo to the moon, and Voyager beyond the planets simply cannot do it. The fuel required would outweigh the payload by factors of millions. Ion drives, which accelerate particles to generate thrust with far greater efficiency, remain too weak for interstellar missions. They can push spacecraft like Dawn and Deep Space One to respectable speeds over years, but nothing approaching the velocities needed to cross light years in human timescales. Engineers have proposed alternatives. Light sails, thin reflective membranes pushed by powerful ground-based lasers could theoretically accelerate tiny probes to 20% of light speed. At that velocity, Alpha Centauri sits 20 years away. A human lifetime becomes long enough to see results. The Breakthrough Starshot initiative has embraced this vision, proposing to send swarms of gram-scale spacecraft toward Alpha Centauri using lasers stationed on Earth. Each probe would be smaller than a smartphone, carrying cameras, sensors and transmitters, accelerating under sustained laser fire until it reached relativistic speeds. But the challenges multiply at every turn. The laser array must deliver gigawatts of power with pinpoint precision across millions of kilometers. The sails must survive the intense heat without warping or tearing. The probes must endure accelerations exceeding 100,000 times Earth's gravity. And after 20 years of flight, they must transmit their findings back across 4 light-years of void, using power sources no larger than a coin. A single error, a single component failure, and the mission becomes a silent ghost racing through the dark. Even if every obstacle is overcome, even if the probes survive the journey and send back images of alien worlds, we face another limitation: communication. A signal from Alpha Centauri takes 4.2 years to reach Earth. Send a message, wait 4 years. Receive a reply, wait another 4. A single conversation spans 8 years. Real-time dialogue becomes impossible. We would be shouting into a well, waiting nearly a decade to hear the echo. And this is the nearest star system. Beyond Alpha Centauri, the distances grow steeper. Barnard's star at 6 light-years, Wolf 359 at 7.9, Sirius at 8.6. Each one adds years to the journey, decades to the communication lag, centuries to the mission duration for conventional spacecraft. The galaxy contains 400 billion stars, and we cannot reach even the closest handful within a human lifetime, even at light speed. So the question becomes sharper. If speed alone cannot save us, what can? Perhaps we build ships large enough to carry entire communities, generation vessels that become travelling worlds, their passengers living and dying across centuries while the ship crawls toward distant suns. Perhaps we freeze human bodies in cryogenic suspension, pausing biological time until arrival. Perhaps we abandon flesh entirely, uploading consciousness into digital substrates that do not age, do not hunger, do not despair at the emptiness. Or perhaps the answer lies not in enduring the journey, but in rewriting the rules. Warp drives that compress space ahead and expand it behind, carrying bubbles of normal space faster than light without violating relativity. Wormholes that tunnel through the fabric of reality, bypassing distance entirely. These ideas sound like fantasy, but they emerge from legitimate physics, from Einstein's equations twisted into unfamiliar shapes. The universe may have loopholes we have not yet discovered, cracks in the cosmic law large enough for a clever species to slip through. Alpha Centauri waits. 3 suns burning in the southern sky, close enough to see with the naked eye, impossibly far away. It is a symbol of everything humanity dreams of reaching, and everything that keeps us trapped at home. The nearest stars are still too far, and light, for all its speed, remains devastatingly slow. Stars within 10 to 20 light-years form a neighbourhood we can almost imagine reaching. Almost. These are the systems close enough that scientists have catalogued them in detail, measured their planets, studied their habitable zones. They are the objects of our most focused dreams, and they remain impossibly distant. Barnard's star sits 6 light-years away, a dim red dwarf racing through space faster than almost any other nearby star. Wolf 359 lies 7.9 light-years out, another red ember glowing faintly in the dark. Sirius, the brightest star in Earth's night sky, burns at 8.6 light-years, a brilliant white beacon visible to every human who has ever looked up. These stars are not abstract points of light. They are destinations, targets, places we have named and studied and yearn to visit. But even at light speed, reaching them consumes years. 6 years to Barnard's, 8 to Sirius, 12 to Tau Ceti, a sun-like star with multiple planets that might, with extraordinary luck, harbour life. And light speed is not possible, not for anything with mass. The energy required to accelerate even a single kilogram to the speed of light grows infinite as you approach that barrier. Physics does not bend on this. It is absolute. Parker Solar Probe, humanity's fastest creation, moves at 192 kilometers per second, 0.6% of light speed. At that velocity, Barnard's star sits 9,000 years away. Sirius demands 13,000. Tau Ceti would require 18,000 years of uninterrupted flight. These are not journeys, they are migrations across time itself, epochs measured not in human generations but in the rise and fall of entire civilizations. The fastest humans have ever travelled is 39,937 km per hour, set by the crew of Apollo 10 during re-entry in May 1969. Gene Cernan, John Young and Thomas Stafford rode a ball of fire through Earth's atmosphere after circling the Moon, their capsule screaming toward the Pacific Ocean at velocities that turned the air around them into plasma. It remains the record for crewed spaceflight, and it is a fraction of 1% of what would be needed to make interstellar travel feasible within a human lifetime. So engineers look elsewhere. If we cannot move faster, perhaps we can endure longer. Generation ships, vast vessels the size of cities, carrying thousands of people across the void for centuries. Each generation born aboard the ship, living their entire lives between stars, passing the torch to children who will do the same until finally, after dozens or hundreds of generations, the ship arrives at a distant sun. The passengers who step onto a new world would be so far removed from the original crew that Earth itself would be mythology. A story told by ancestors no one remembers. This is not science fiction. This is the only realistic option we currently have for crewed interstellar travel. Build a ship large enough to sustain a closed ecosystem. Launch it with enough resources to last centuries. Hope that the social structures aboard remain stable across generations, that the machinery does not fail, that the destination proves worth the journey when descendants finally arrive. Cryogenic suspension offers another path. Freeze human bodies, slow metabolism to near zero, wake the crew decades or centuries later when the destination nears. The technical challenges are immense. Ice crystals form in cells during freezing, tearing apart delicate structures. Organs fail. Brains suffer irreversible damage. No mammal larger than a hamster has ever been frozen and revived successfully, but research continues. If the problems can be solved, if human tissue can be preserved and awakened intact, then the subjective experience of travel collapses. You close your eyes near Earth and open them decades later orbiting another star, or we abandon flesh entirely. Digital consciousness, human minds uploaded into computational substrates that do not age, do not require food or air or warmth. A computer can wait centuries without concern. It can endure radiation, vacuum, temperatures that would kill any biological organism instantly. If the mind is information, and information can be copied and stored, then perhaps the answer is not to send humans across the stars, but to send the patterns that make us human and reconstruct bodies on the far side. These are the options when light speed proves too slow and faster options remain theoretical. Wait, sleep, transcend. Each carries costs and uncertainties that make the journey itself seem secondary. But the alternative is staying home forever, trapped on a single world circling a single star, watching the universe through telescopes while knowing we can never touch it. Decades become the minimum currency of interstellar travel. Not hours or days or even years, but spans of time that outlast careers, that consume entire phases of human life. And this is only for the nearest stars, the handful within 20 light years. Beyond that, the numbers grow steeper, 50 light years, 100, 1,000. Each step outward adds centuries to the journey at current velocities, centuries we do not have, centuries that erode hope into something harder and colder. The universe is vast. Light, for all its speed, crawls across it, and we, bound by physics and biology, are slower still. For decades, astronomers have searched the skies for planets that orbit within the habitable zone of their stars, that narrow band of distance where temperatures allow liquid water to exist on a world's surface. Water is the signature molecule of life as we know it. Where there is water, there might be chemistry complex enough to spark biology. And so, the search continues. Telescopes scanning thousands of stars, measuring the faint dips in brightness as planets cross in front of their suns. The discoveries have been staggering. Thousands of exoplanets confirmed, hundreds sitting in habitable zones, dozens that might, with extraordinary fortune, host oceans and atmospheres and perhaps even life. Proxima Centauri has one, a rocky world orbiting its dim red star at just the right distance to allow liquid water. TRAPPIST-1, 40 light years away, hosts 7 Earth-sized planets, 3 of them in the habitable zone. Kepler-4-5, 2b, a super-Earth orbiting a sun-like star 1,400 light-years distant. The galaxy is rich with possibility. dense with worlds that could harbour life, and every single one is unreachable. Even at light speed, Proxima b demands 4.2 years of travel. TRAPPIST-1 requires 40 years. Kepler-4, 5. 2b sits 14 centuries away at the ultimate cosmic speed limit. These are not journeys, they are epochs. The time required to reach even the nearest potentially habitable world exceeds the duration of most human careers. The time to reach more distant candidates spans generations, civilizations, entire phases of recorded history. Communication adds another layer of impossibility. A message sent to Proxima b takes 4.2 years to arrive. If an intelligent species there replied instantly, we would wait 8.5 years for the answer. A single exchange of information, one question, and one response consumes nearly a decade. Real-time conversation becomes a fantasy. You send your message and hope that whoever receives it decades or centuries later chooses to respond, knowing you may not live long enough to hear the reply. For missions travelling at relativistic speeds, the problems multiply. Time dilation means clocks aboard the spacecraft run slower than clocks on Earth. A traveller might experience only months while years pass outside. But this does not solve the communication problem, it worsens it. Messages sent from Earth toward a spacecraft moving near light speed face an event horizon beyond which they can never catch up. If the message is sent too late, the spacecraft remains forever ahead, racing away faster than the signal can close the gap. From the traveller's perspective, Earth goes dark. Silence replaces dialogue. Signals sent from the spacecraft back toward Earth or toward a destination suffer similar constraints. During the cruise phase, when the ship accelerates to relativistic velocity, all messages pile up, arriving at the destination only moments before the craft itself. There is no gradual exchange of data, no updates during the journey. Everything arrives in a burst, a flood of information compressed into the final moments before landing. For long missions, this means decades or centuries of radio silence, punctuated by a single overwhelming transmission. The implications are stark. Interstellar spacecraft must operate autonomously. They cannot rely on Earth for guidance. They cannot wait for instructions when problems arise. If a system fails, if a course correction becomes necessary, if an unexpected obstacle appears, the crew or onboard computers must solve it alone. Help from home, even if it were sent immediately, would arrive years too late. The spacecraft becomes an island, cut off from the rest of humanity by distance and the unyielding speed of light. This reality shapes every aspect of mission design. Robotic probes, which require communication only during landing, face manageable challenges. They can travel in silence, gathering data, storing it aboard until the destination nears, and transmission becomes possible. Crewed missions demand far more. Humans want contact, they crave updates, reassurance, the knowledge that Earth remembers them. But physics offers no comfort. For crews travelling to distant habitable worlds, isolation becomes absolute. They depart knowing they may never speak to Earth again during the cruise phase. They arrive at their destination only to face years more delay before anyone back home learns of their success or failure. The habitable zone planets we have discovered are treasures, worlds that might hold oceans, storms, life. Places where humanity could, in theory, establish new homes among the stars. But they sit beyond our grasp, separated from us by gulfs so vast that light itself struggles to cross them. We see them through telescopes, measure their atmospheres, calculate their masses, and we cannot reach them. Not in a human lifetime, not even close. So the search continues, not for the nearest habitable world, but for a way to cross the impossible distance. Generation ships that turn spacecraft into travelling civilizations. Cryogenic sleep that freezes time for the crew while the universe ages around them, or something more radical. Warp drives that sidestep the light speed barrier entirely. Wormholes that punch holes through space. Technologies that sound like dreams but emerge from the same equations that govern everything else. The habitable worlds are out there, waiting. But unless we find a way to bend the rules, they will remain forever on the far side of an uncrossable ocean. Among all the star systems charted by astronomers, TRAPPIST-1 stands alone as a beacon of hope and frustration. It is a small, cool red dwarf sitting 40 light-years away in the direction of the constellation Aquarius. Around it, 7 rocky planets circle in close ballet. 3 of them orbiting in the precious habitable zone where liquid water might survive. This system, discovered only recently, called to us on a primal level. Not just one possible home, but 7 in a single family of the worlds. If Earth were scaled to the size of a marble, TRAPPIST-1 would be a cold red ember drifting more than 1,000 kilometers away. Even light, moving at its ultimate velocity, would need 40 years to cross that gulf. If we sent a message tonight and waited for an answer, each exchange would take 80 years, the span of a human lifetime committed to a single conversation. A child could ask a question in her youth and live an entire life before hearing an answer. The challenge is not merely distance, but the implications of being so far from home. For a probe, perhaps a wafer-thin laser-driven light sail, at 20% of light speed the crossing would last 2 centuries. For a human crew, the journey means surrendering all ties to Earth. Generations would live and die, cultures would evolve in isolation, and any notion of returning home would collapse into myth. TRAPPIST-1's 7 worlds are a feast for the imagination, but a famine for ambition. Communication across this gulf is as daunting as the travel itself. Years-long delays mean signals must be planned with care. A probe cannot rely on Earth for guidance or rescue. Once it launches, it sails into cosmic darkness, forced to improvise, solve every crisis alone, and deliver its findings only at the journey's end. If any of its precious transmissions fail to thread the gap on arrival, the discovery is lost to silence forever. And the physics are merciless. Light is the limit. Even in theory, no ship could exceed it. Unless we discover new laws, wrinkle space, open wormholes, ride on a ripple of warped geometry, 40 years remains the inviolable minimum, eternity on a human scale. TRAPPIST-1's 7 worlds capture the endless yearning of our species. They tease us with the possibility of oceans, atmospheres, life, each world new, alien, and waiting. They show us the promise of a universe teeming with places to go, and yet each world remains locked behind a wall of dark, stubborn immensity. The real heartbreak is not that we see them, but that with all we know and all we dream, they are still forever out of reach, unless we dare to find new ways to break the rules. Within 100 light-years of Earth, the galaxy begins to feel crowded. Thousands of stars burn in this sphere, scattered across the darkness like grains of sand on a beach. Many harbour planets. Some orbit in habitable zones. A few might hold oceans, continents, atmospheres breathable to life we could recognise. This is the neighbourhood where dreams of interstellar colonisation begin to feel almost tangible, where science fiction brushes against the edges of possibility. But 100 light-years is not a neighbourhood. It is an abyss. At light speed, a journey to the far edge of this sphere consumes a full century. 100 years of continuous travel at the ultimate velocity the universe allows, and you arrive at a single star on the boundary. Not the centre of the galaxy, not a distant cluster, just the outer limit of what we might optimistically call our cosmic backyard. Every star beyond that mark adds more decades, more generations, more centuries to the crossing. Parker Solar Probe, humanity's fastest creation, moves at 192 kilometers per second, barely 0.6% of light speed. At that velocity, 100 light-years translates to over 15,000 years of flight. 15 millennia. Longer than all of recorded human history. Longer than agriculture, cities, writing, empires. If such a probe had launched when the first humans painted caves in Lascaux, it would still be en route today, having crossed less than a fraction of the distance. Helios 2, which held the speed record for nearly 50 years before Parker surpassed it, reached 70 kilometers per second. 100 light-years at that pace demands over 40,000 years. Voyager 1, drifting through interstellar space at 17 kilometers per second, would need more than 170,000 years. These are not timescales. They are geological ages, spans of time in which species evolve and continents drift. And yet, within this sphere, we have identified hundreds of potentially habitable worlds, rocky planets circling stars similar to our Sun, super-Earths orbiting red dwarfs in tight, warm embraces, gas giants with moons that might hide liquid water beneath icy crusts. Each discovery adds another pin to the map, another destination that taunts us with proximity and impossibility. We see them, we measure them, we model their climates, estimate their surface conditions, speculate about their potential to harbour life, and we cannot reach them. The problem is not merely speed, it is energy. Accelerating even a small spacecraft to a meaningful fraction of light speed requires power that dwarfs anything humanity has built. The fastest spacecraft we've created, Parker Solar Probe, achieved its record velocity not through onboard propulsion, but by falling toward the Sun, using gravity to slingshot itself to extreme speeds. This technique works within a solar system, where massive bodies like planets and stars can provide gravitational assists. It fails utterly in the void between stars, where there is nothing to push against, nothing to fall toward, only the empty dark stretching in all directions. Engineers have proposed light sails, thin reflective membranes pushed by powerful lasers stationed on Earth or in orbit. These sails, spanning tens or hundreds of meters, would catch photons like wind, accelerating slowly but steadily until they reach 20% of light speed or more. At that velocity, 100 light-years becomes 500 years, still beyond a human lifetime but within the span of a long-lived civilization. Gram-scale probes could be sent in swarms, racing toward distant stars, gathering data, transmitting findings back across the void. But even this vision carries immense challenges. The laser arrays must deliver gigawatts of power with precision across millions of kilometers. The sails must survive the intense heat without warping. The probes must endure accelerations measured in thousands of g-forces and operate for centuries without maintenance or repair. And after all that, after 500 years of flight, the data they send back takes another century to reach Earth at light speed. You launch a mission and die long before the first image arrives home. The 100 light-year wall is not a physical barrier, it is a temporal one. It is the boundary where human ambition collides with human mortality, where the gulf between what we can see and what we can touch becomes so vast that no single generation, no single civilization can hope to cross it using conventional means. Beyond this wall, the stars become monuments to patience and longing, destinations we can name but never visit, worlds we can imagine but never explore. So we return to the same question that haunts every section of this journey. If speed alone cannot save us, what can? Perhaps we build vast generation ships, entire societies sealed in metal and glass, drifting through the void for centuries while descendants born in transit finally reach the destination their ancestors dreamed of. Perhaps we freeze ourselves, pausing time through cryogenic suspension, waking centuries later to a universe that has aged while we remained still. Or perhaps the answer lies not in enduring the journey, but in rewriting the rules entirely, warp drives that compress space, wormholes that tunnel through reality, technologies that sound like fantasy but might be the only way to escape the prison light speed has built around us. 100 light-years, thousands of stars, hundreds of worlds, and every single one beyond the reach of any technology we possess. The wall stands, and light, for all its speed, remains devastatingly, impossibly slow. Step back, look up. Every star visible to the naked eye on a clear night belongs to our galaxy, the Milky Way. It stretches across the sky like a river of light, a band of billions of suns spread across 100,000 light-years or more. This is not a small neighborhood. This is not a cluster we can hope to map completely in a human lifetime. This is a vast island of stars, gas, and darkness, a structure so immense that even light takes 100 millennia to cross from edge to edge. 100,000 years at the speed of light. Parker Solar Probe, moving at 192 kilometers per second, would need over 150 million years to traverse the galaxy. 150 million years, longer than the age of the dinosaurs, longer than most species persist on Earth. If such a probe had launched when the first vertebrates crawled onto land, it would still be travelling today, having barely scratched the width of the Milky Way. Voyager 1, drifting through interstellar space at 17 kilometers per second, faces an even more staggering timeline. To cross the galaxy at that speed would take over 1.7 billion years. The Earth itself is only 4.5 billion years old. By the time Voyager completed its journey, entire geological eras would have passed. Continents would have merged and split. New mountain ranges would have risen and eroded to dust. The sun would have aged, brightened, perhaps even begun its death throes. This is the prison we inhabit. The Milky Way is our home, a galaxy of 400 billion stars and we are confined to a single point within it. Earth orbits the Sun 26,000 light-years from the galactic centre. We sit far out in the suburbs, in a quiet arm of the spiral, surrounded by stars we can see but not reach. The core, where millions of stars cluster in dazzling density around a supermassive black hole, remains impossibly distant. 26,000 years at light speed, nearly 4 million years aboard Parker Solar Probe, over 150 million years aboard Voyager, and the galaxy is not static. It rotates, a massive wheel of stars and gas turning slowly around its centre. Our Sun, along with its planets, completes one orbit every 225 million years. This is called a galactic year, a timescale so vast it dwarfs human comprehension. The last time Earth occupied this position in space, the dinosaurs had not yet appeared. The next time we return here, assuming humanity survives, we will be a species unrecognizable from what we are now. Within the Milky Way, distances become nearly meaningless. The nearest star, Proxima Centauri, sits 4.2 light-years away. The farthest stars in our galaxy lie 50,000 light-years distant or more. Between these extremes, hundreds of billions of stars drift in the dark, each one a potential destination, each one separated from us by gulfs so vast that light itself struggles to bridge them. Engineers dream of solutions, generation ships large enough to sustain entire communities for millennia. Massive vessels propelled by nuclear fusion or antimatter, crawling across the galaxy at fractions of light speed while generations live and die aboard. These ships would be worlds unto themselves, carrying ecosystems, cultures, histories spanning centuries. Their passengers would be born into the journey, live their entire lives between stars, and die knowing their descendants might reach the destination someday. Or we turn to more radical concepts. Warp drives that compress space in front of a ship and expand it behind, allowing the vessel to move faster than light without violating relativity, because it is not the ship moving through space, but space itself moving around the ship. The mathematics suggest this might be possible, but only with exotic matter possessing negative energy density, something we have never observed and may not exist. Still, the equations allow it, and where physics permits, humanity dares to dream. Wormholes offer another theoretical escape. Tunnels through the fabric of space-time, shortcuts connecting distant regions of the galaxy. Enter one end near Earth, emerge light years away moments later. Einstein's equations predict their existence, but they remain purely theoretical. We do not know how to create one, how to stabilize one, or whether they exist naturally anywhere in the universe. They are tantalizing possibilities, doors drawn on the walls of our cosmic prison, but doors we cannot yet open. The Milky Way is a cage of distance. We see its structure from within, tracing the spiral arms with telescopes, mapping the positions of billions of stars. We know where the densest regions lie, where new stars are being born in clouds of gas and dust, where old stars drift in quiet orbits far from the chaos of the core. And all of it remains beyond our reach, not because we lack the will or the vision, but because the galaxy is simply too vast and light. The fastest thing in the universe is devastatingly, impossibly slow. If we are ever to explore beyond our immediate neighbourhood, we must find a way to bend the rules. Speed alone will not save us. Even at light speed, the galaxy is a lifetime away. At the velocities we can currently achieve, it is epochs. So we turn our minds toward the impossible, toward technologies that sound like fantasy but may be the only way forward. Warp drives, wormholes, suspended animation, digital consciousness, generation ships that turn travel into a way of life rather than a means to an end. The Milky Way stretches above us every night, a promise and a reminder. A promise that the universe is vast and filled with wonders, a reminder that we are small, slow, and bound by laws we did not write. The stars call to us, and we, trapped by the speed of light, can only listen. Turn your gaze toward the centre of the Milky Way. There, hidden behind clouds of gas and dust, lies a region so dense with stars that the night sky would never fall truly dark. Millions of suns crowd within a few light years of each other, orbiting a supermassive black hole 4 million times the mass of our Sun. This is Sagittarius A star, the gravitational anchor around which the entire galaxy wheels. From Earth, this core sits 26,000 light-years away. 26,000 years at the speed of light, not decades, not centuries. Millennia stacked upon millennia, epochs that span the entire history of human civilization repeated more than twice over. If light departed the galactic centre when our ancestors painted caves and carved bone, it would arrive at Earth today, carrying images of a cosmic heart we can never hope to visit. Parker Solar Probe, racing at 192 kilometers per second, would need nearly 4 million years to reach the core. 4 million years. Homo sapiens as a species is only 300,000 years old. Modern humans with art and language and agriculture have existed for perhaps 50,000. Parker would fly for 80 times longer than our entire history as modern humans, just to glimpse the centre of our own galaxy. Voyager 1, at 17 kilometers per second, faces a journey of over 46 million years. The dinosaurs ruled Earth for 165 million years. Voyager's trip to the galactic core would consume more than a quarter of that span. The continents would shift, ice ages would come and go, new species would evolve, flourish, and vanish into extinction, and still Voyager would be crossing the silent dark between here and there. The core is not merely distant, it is violent. Stars there orbit so tightly that close encounters rip solar systems apart, flinging planets into the void. Some stars are accelerated by the black hole's gravity to speeds exceeding 1,700 kilometers per second, nearly 1% of light speed. These hypervelocity stars tear away from the galactic center and race outward through the Milky Way, faster than any human-made object has ever moved. One such star, discovered recently, is hurtling through space at such extreme velocity that it will eventually escape the galaxy entirely, becoming a lone wanderer in the intergalactic void. If nature can accelerate stars to 1% of light speed through gravitational interactions with black holes, it raises a tantalizing question. Could we harness similar forces? Could spacecraft be designed to dive close to massive objects, using their gravity to slingshot toward impossible velocities? Parker Solar Probe already does this on a modest scale, using Venus and the Sun to reach its record-breaking speed. But the energies near the galactic core dwarf anything in our solar system. A civilization capable of navigating that environment, of surviving the radiation and tidal forces, might achieve speeds we can only dream of. But we're not that civilization. We are 26,000 light-years away, separated from the core by a gulf so vast that even contemplating the journey feels absurd. The centre of our galaxy, with its black hole and its dense stellar neighbourhood, remains a concept, an idea, a target we can observe through telescopes but never touch. And the core is just one point in the Milky Way. The galaxy contains 400 billion stars spread across 100,000 light-years or more, each star a potential destination, each one separated from us by distances that mock human ambition. We dream of exploring the galaxy, of mapping its structure, of visiting its wonders. But light speed is too slow, and we cannot even approach light speed, so we turn once again to ideas that sound impossible. Generation ships that transform space travel into a way of life, where generations are born, live, and die aboard vessels crawling across the void. Suspended animation that freezes time for the crew while the universe ages outside. Digital consciousness uploaded into machines that do not tire, do not age, do not despair at the vast emptiness. Or technologies that sidestep the problem entirely, warp drives folding space, wormholes punching shortcuts through reality, methods that might allow us to reach the core not in millions of years, but in lifetimes or less. The galactic core waits, a maelstrom of stars and darkness, spinning around a black hole older than Earth itself. It is the heart of our galaxy, the place where everything began, the anchor that holds 400 billion suns in their orbital dance. And it is forever out of reach unless we find a way to break the rules, to bend physics in ways we do not yet understand. The core is not just distant, it is a monument to the limits of speed, a reminder that even light, the fastest thing in existence, is devastatingly, impossibly slow. Look to the northeast on a clear autumn night and you can see it with the naked eye, a faint smudge of light against the darkness. This is Andromeda, the nearest major galaxy to the Milky Way, a spiral island of 1 trillion stars sitting 2.5 million light-years from Earth. It is the most distant object visible without a telescope, a monument to the scale of the universe and the limits of human reach. 2.5 million years at the speed of light. If a photon left Andromeda when our earliest human ancestors walked upright in Africa, it would arrive at Earth today. 2.5 million years ago, Homo habilis chipped the first stone tools. Ice ages came and went, continents shifted, species evolved, flourished and vanished, and through all of it, light from Andromeda travelled across the void, moving at the ultimate speed the universe allows, only now reaching our eyes. Parker Solar Probe, at 192 kilometers per second, would need over 3.9 billion years to reach Andromeda. 3.9 billion years. The Earth is 4.5 billion years old. Parker would spend nearly the entire lifetime of our planet making the crossing. When it finally arrived, if anything could survive such a journey, the Earth itself would be unrecognizable. The Sun would have aged. The continents would have merged into new configurations. Life would have evolved into forms we cannot begin to imagine. Voyager 1, drifting at 17 kilometers per second, faces a journey of over 44 billion years. The universe itself is only 13.8 billion years old. Voyager would need more than 3 times the current age of existence to reach Andromeda. By the time it arrived, the universe would have expanded beyond recognition. Stars we see today would have died. New generations of stars would have formed, lived and burned out. Galaxies would have collided, merged, scattered. The cosmos itself would be older, colder, darker. And Andromeda is close. Cosmically speaking, it is our neighbour. It sits within the local group, a collection of more than 50 galaxies bound together by gravity. Beyond the local group lie thousands more galaxies within 100 million light-years, millions within a billion, billions scattered across the observable universe, each one farther than the last, each one more impossible to reach. Andromeda is also approaching. Gravity pulls it toward the Milky Way at roughly 110 kilometers per second. In about 4 billion years, the two galaxies will collide, their stars mingling in a cosmic dance that will reshape both into a single elliptical giant. We will not be here to see it. The Sun will have swelled into a red giant by then, consuming the inner planets, rendering Earth uninhabitable long before the collision occurs. But the approach continues, inexorable. 2 massive islands of stars drifting together across the void. Even this approach, spanning billions of years, highlights the paradox. Andromeda moves toward us at 110 kilometers per second. Parker Solar Probe moves at 192 kilometers per second. The fastest human-made object is less than twice as fast as a galaxy, drifting through space under the influence of gravity. We can build machines that approach the velocity of cosmic motion, but we cannot exceed it by enough to matter. The gap between what we can achieve and what we need is not a factor of 2 or 10. It is a factor of thousands, millions. We would need to move at tens of thousands of kilometers per second, a significant fraction of light speed to make interstellar travel feasible. And even light speed, as we have seen, is devastatingly slow, so we return to the same recurring question. If conventional speed cannot save us, what can? Perhaps we learn to fold space, to compress the distance between here and there until it becomes traversable. The Alcubierre warp drive proposes exactly this. A bubble of normal space carried faster than light by the expansion and contraction of space-time around it. The ship inside the bubble remains stationary relative to its local frame, never violating relativity, while the bubble itself moves at any velocity we choose. But such a drive requires exotic matter with negative energy density, something physics allows mathematically, but which may not exist in reality. Wormholes offer another theoretical path. Einstein's equations permit tunnels through space-time, shortcuts connecting distant regions. Step into one end near Earth, emerge from the other near Andromeda, bypassing the 2.5 million light-years entirely. But wormholes, if they exist, would require enormous energy to create and stabilize. We have no idea how to build one, or whether they occur naturally anywhere in the universe. They remain speculations, beautiful possibilities drawn on paper, doors that may not exist. Or perhaps we abandon the idea of travelling ourselves. Send probes instead. Tiny gram-scale spacecraft accelerated by ground-based lasers to 20% of light speed. At that velocity, Andromeda sits 12.5 million years away. Still impossibly long, but within the potential lifespan of a durable machine. The probe could gather data, transmit findings back across the gulf, and continue onward into the darkness beyond. By the time its signals reached Earth, millions of years later, humanity might be extinct, evolved into something unrecognizable, or thriving among the stars. The probe would be a message in a bottle, cast into an ocean so vast that even waves of light take epochs to cross. Andromeda hangs in the night sky, a smudge of ancient light. It is close enough to see but too far to touch. It is a reminder that the universe operates on scales that dwarf human ambition, that even our grandest dreams of exploration collide with the immovable wall of distance and time. 2.5 million light-years, and light for all its speed remains heartbreakingly impossibly slow. Andromeda does not drift alone. It belongs to the Local Group, a gravitationally bound collection of more than 50 galaxies spread across roughly 10 million light-years. The Milky Way and Andromeda dominate this cluster, two massive spirals accounting for most of the group's mass. The rest are smaller satellites, dwarf galaxies orbiting the giants, irregular clouds of stars, faint smudges barely visible even with powerful telescopes. 10 million light-years. This is the neighbourhood in which our galaxy lives, the cosmic community to which we belong, and every member sits impossibly far away. Triangulum, the third largest galaxy in the Local Group, lies 3 million light-years from Earth. The Large Magellanic Cloud, a satellite of the Milky Way visible from the southern hemisphere, sits 160,000 light-years distant. The Small Magellanic Cloud hovers at 200,000 light-years. These are our closest galactic neighbours, structures massive enough to contain billions of stars, and they remain completely unreachable by any technology we possess. Parker Solar Probe, at 192 kilometers per second, would need over 24 billion years to reach Triangulum. 24 billion years. The universe itself has existed for only 13.8 billion. Parker would require nearly twice the current age of reality to cross the gap. The stars we see today would be long dead. New galaxies would have formed, collided, evolved. The cosmos would be colder, darker, more diffuse. Voyager 1 faces an even more staggering timeline, over 270 billion years to reach Triangulum at 17 kilometers per second. By then, the universe will have aged beyond recognition. Star formation will have slowed to a trickle as gas reserves deplete. Most galaxies will have merged into massive ellipticals or drifted apart in the expanding void. The sky will be darker, emptier, lonelier. And Voyager will still be crossing the space between galaxies, a relic from an earlier, brighter age of the cosmos. The Local Group represents a boundary of sorts. These 50 galaxies are gravitationally bound, meaning they will not drift apart as the universe expands. They orbit a common centre of mass, held together by their collective gravity against the outward pull of cosmic expansion. In billions of years they will merge, colliding and coalescing into a single massive elliptical galaxy sometimes called Milkomeda. But this process takes epochs. The galaxies approach slowly, their motions measured in millions of years, and we, sitting within one of them, cannot reach even the nearest members of our cluster. Beyond the Local Group, the universe changes. Galaxies there are not bound to us. They drift away, carried by the expansion of space itself, receding faster the farther they lie. At great enough distances, galaxies move away from us faster than light, not because they violate relativity, but because space itself stretches between us and them. No spacecraft, no matter how fast, can ever reach these galaxies. They sit beyond a cosmic event horizon, destinations that physics forbids us from ever visiting. But even within the Local Group, where galaxies remain gravitationally tethered, the distances overwhelm any attempt to cross them. 10 million light-years. If we could somehow achieve 10% of light speed, an absurd goal given current technology, the crossing would still take 100 million years. 100 million years ago, dinosaurs roamed Earth. Mammals were small, insignificant creatures hiding in the shadows. If a spacecraft had launched then at 10% light speed, it would arrive at the far edge of the Local Group today, and Earth would be utterly transformed. Engineers dream of solutions. Light sails accelerated by ground-based lasers to 20% of light speed could, in theory, reach nearby galaxies in tens of millions of years. These sails would be tiny, gram-scale probes carrying minimal instruments, transmitting data back across the void. but even 20% of light speed represents a monumental engineering challenge. The laser arrays required would dwarf anything humanity has built. The sails would need to survive accelerations measured in tens of thousands of g-forces, and the probes, once launched, could never be recalled, never be repaired, never be upgraded. They would race into the darkness, alone, carrying the hopes of a species that will be extinct long before they reach their destinations. Or perhaps we turn to more radical concepts. Warp drives that fold space, allowing faster than light travel without violating relativity. Wormholes that tunnel through the fabric of reality, bypassing distance entirely. These ideas emerge from legitimate physics, from Einstein's equations twisted into unfamiliar shapes. They sound like fantasy, but they may represent the only path forward. If conventional speed cannot save us, we must find ways to rewrite the rules, to sidestep the limitations physics has imposed. The local group is our cosmic home, a cluster of galaxies bound together by gravity in an expanding universe. It is vast beyond human comprehension, spanning 10 million light-years, containing trillions of stars, and every single galaxy within it sits beyond our reach. Not because we lack the will or the ambition, but because the universe is simply too large, and light, the fastest thing in existence, is devastatingly, impossibly slow. We can see our neighbours, we can study them, measure them, map their structures, but we cannot touch them. The local group is a neighbourhood we will never visit, a community we will never join, a family we can observe only from afar. Beyond the boundaries of our local group lies a realm so immense that the word cluster does not convey its reality. The Virgo supercluster is a tapestry of thousands of galaxies, woven together by the quiet pull of gravity, stretching 65 million light-years across the darkness. Within its core, the Virgo cluster itself contains over 2,000 galaxies, giants, dwarves, spirals, ellipticals, all spinning in elaborate patterns set in motion over billions of years. 65 million light-years is not just a distance, it is an era. At light speed, you would need 65 million years to traverse this supercluster from edge to edge. When the journey began, dinosaurs would have just vanished from Earth, wiped away by a falling asteroid and the onset of a new era. The continents would reshape themselves, the world would bloom into its present form, civilizations would rise, fall and rise again as you sailed blindly toward a galaxy halfway across the supercluster. And yet, this tapestry is merely the local expanse. The Virgo supercluster is only one of many. Beyond it, the universe expands in every direction, clusters of clusters forming walls, filaments, voids, structures spanning hundreds of millions of light-years. Each supercluster, each knot in the cosmic web is separated by gulfs so vast that the concept of distance dissolves into pure abstraction. The observable universe itself is 46 billion light-years in radius, containing everything light has reached us since the dawn of time. Could we ever visit these galaxies? At our fastest achieved velocities, Parker Solar Probe's astounding 692,000 km per hour, crossing the supercluster would still take over 100 billion years. That is 7 times longer than the age of the universe. At these scales, even light loses its power to connect. The vast structures revealed by telescopes remain forever beyond our touch. Cataclysmic forces shape the supercluster. Galaxies collide, merge, consume one another. Clusters crash together, inflating clouds of gas that burn hotter than any star. Streams of dark matter wind invisibly among the visible galaxies, sculpting structures that only mathematical models can reveal. The supercluster is alive, restless, and utterly unreachable by any technology we can imagine. The mind craves a loophole, a way out. Perhaps, if we could master space-time itself, wormholes could bridge the gaps between clusters, shortcuts cutting straight through the empty deserts between galaxies. Or maybe, somewhere within the equations of General Relativity, a method waits for us to fold or tunnel through the fabric of the universe, rendering millions of light-years trivial. But for now, these remain dreams painted on chalkboards, proofs, and speculations. We are locked inside a local bubble on the edge of greatness, able to see the cosmic landscape but never to walk it. The Virgo supercluster and all the vast scaffolding beyond stand as monuments to the power and the slowness of light, and to the stubborn laws that bind our reach. We look outward, across millions of light years, and the universe patiently waits, unmoved, for a breakthrough in imagination, physics, or hope. The Virgo supercluster is vast, but what comes next is almost unfathomable. The observable universe is a sphere with a diameter of about 93 billion light-years. Within this cosmic bubble, there may be as many as 2 trillion galaxies, giants, dwarfs, spirals, and elliptical swarms stretching across scales that dwarf every supercluster, every local group, every star the human eye can see. These are the galaxies whose light has managed to reach us since the birth of the universe, arriving after journeys lasting more than 13 billion years. And even that immense bubble is just what we can see. The actual universe may be vastly larger, perhaps infinite, filled with regions beyond any conceivable reach. The centre of this sphere is Earth, not because we are special, but because the observable universe is defined by what light has had time to travel since the Big Bang. In every direction, light from objects 46 billion light-years away reaches us now, only because space itself has stretched during their journey, carrying those galaxies farther away as the light crossed the expanding cosmos. To cross this sphere at the speed of light would require 93 billion years. The universe itself is only 13.8 billion years old. But cosmic expansion means that objects which emitted their light at the birth of the universe are now tens of billions of light-years farther than where they started. We receive them as they were, not as they are. The farther we look, the older the image, and the deeper into cosmic history we peer. Consider Parker Solar Probe, humanity's fastest emissary, at 192 kilometers per second. Crossing the observable universe at that speed would take over 160 trillion years. 160 trillion years, 10,000 times older than the current age of everything. At these scales, even the concept of travel loses meaning. Every known era, every geological and biological change would occur and vanish. The stars above would evolve and fade and die, all while our hypothetical probe moved through a fraction of the bubble. Within the observable universe, the numbers turn astonishing. There are more stars than grains of sand on Earth's beaches. More planets, more cosmic destinations than any dreamer could count. The laws that govern their distances, the cosmic speed limits, mean that almost all will remain unvisited. The expansion of space itself ensures that most galaxies are now receding from us faster than light, not because they break the laws of physics, but because space stretches, carrying them onward. Many will never be able to send a photon our way again. This is the final measure of vastness and isolation. The edge of the observable universe is not a wall we can breach. It is a horizon we will never cross, not in lifetimes, not in civilizations, not even at light speed. The mysteries that wait beyond float forever out of reach, part of a story we are only allowed to watch from our distant little island, lit by ancient photons. If we ever hope to see farther, go deeper, become more than a cosmic observer, we must find loopholes, exotic cracks in the speed limit, tunnels through space-time, radical methods to sidestep the laws that cage us. Until that day, the edge of observable reality remains a beautiful eternal silence, lit by the oldest light, defined by the slowest journeys, measured by a speed that, for our ambitions, is simply not enough. Stars burn with ancient light, beacons that have persisted for millions and billions of years. Their life cycles stretch far beyond the brevity of human existence, emphasizing the gulf between the cosmos and our fleeting time on Earth. Small stars, like our Sun, live for around 10 billion years, quietly fusing hydrogen into helium in a steady pulse of energy. More massive stars blaze briefly but brilliantly, lasting only millions of years before exploding in supernovae that scatter their enriched guts across space to seed new stars and planets. Compared to these lifetimes, the journeys between stars at light speed are long but not eternal, at least within the scale of stellar epochs. Yet, the window for life itself on many planets may be shorter. Habitable conditions depend on a delicate balance of temperature, atmosphere and radiation, qualities that can shift dramatically over a star's life cycle. A star nearing the end of its hydrogen-burning phase expands into a red giant, vaporizing nearby planets or rendering them uninhabitable. The longevity of a star dictates the maximum time available for life on orbiting worlds. When vessels travel at speeds well below light, Crossing even the nearest stars stretches into decades, centuries, or millennia, durations surpassing a human lifetime many times over. Even generation ships, in which entire populations live and die aboard starships during the voyage, challenge the concept of continuity for civilizations and cultures. The ship becomes an ark, a miniature world drifting through emptiness as generations are born, live, perish, and pass on. Stars live on timescales that dwarf such human constructs. The journey to the nearest stars may take a few hundred or thousand years today's technology might allow, but their longevity offers some hope. Life could survive across centuries or millennia if protected aboard ships or in suspended animation. However, many stars are older or younger than their neighbours, and their planets may or may not currently harbour life. The cosmic clock ticks differently around each star. Farther out, on galactic scales, travel times grow to millions of years. Entire yet unknown civilizations could arise and vanish within that span, their stories forever lost in darkness. By the time we arrive, we may find ruins, or nothing at all. Stars live long lives, but they do not last forever, and travel between them requires patience beyond human experience. Ultimately, the lifetime of stars sets a cosmic clock against which travel must be measured. Light speed is fast in human terms but slow in astronomical terms. Stars endure beyond our reach, but their lives impose limits on when and where life can flourish. Crossing the universe at light speed is crossing a river of time as much as a gulf of space, a journey governed by both distance and the life cycles of the very stars we dream to reach. This cosmic perspective deepens the challenge and the mystery. We are travellers not just of space, but of time, bound to the rhythm of stars that shine for epochs beyond human dreams, yet will eventually fade, leaving only their light as echoes of a vanished past. Imagine the vast gulf separating even the nearest stars, a road so long and empty that no single human lifetime could ever traverse it. Travel to nearby stars, even at fractions of light speed, demands decades or centuries, lifetimes lost to the void. This is the generational void, the span of time we must face if we dream of becoming interstellar travellers. Generation ships are humanity's answer to this immense challenge. Massive vessels, self-contained worlds capable of sustaining entire populations for hundreds or even thousands of years. A floating city or a travelling ecosystem embarking on a journey across endless dark, where those who launch may never see the destination. Their children and grandchildren, born and raised aboard, inherit the mission, gripping the fragile hope that distant suns await. These ships become more than vessels. They become societies unto themselves. Histories will unfold internally, independent of Earth. Cultures will evolve, religions form, laws change. The generational void stretches beyond travel time. It endures inside the ship. The fabric of human life contorts to accommodate centuries of passage through silence and dark. But the void is not measured only in time, it is isolation. Communication with Earth becomes impossible. The light speed limit governs dialogues across space. A message sent to a ship 50 light-years distant takes 50 years to arrive, and decades more for the reply. The ship drifts in silence as centuries pass outside. Engineering challenges multiply. Life support systems must function without fail for centuries. Food, water, air, billions of cycles sustained with no outside replenishment. Psychological pressures grow. Communities must survive social stresses, conflicts, boredom. Whether the genetic diversity is sufficient to avoid degradation over generations remains a concern. The generational void is as much a question of biology and sociology as physics. Suspended animation offers a half measure, frees humans in stasis, slowing or halting biological time. Yet, even the most advanced cryogenics confront the brutal reality. Freezing damages cells. Reviving multitudes safely remains a barrier, but if solved, travellers could skip across decades or centuries as if they were moments. Digital consciousness ventures further into the void, uploading minds into machines immune to aging or environmental hardship. A digital traveller journeys not in flesh but as data, preserving memories, thoughts, identity. Here survival becomes less biological, more informational. The generational void contracts, time distorts, the traveller sleeps through centuries yet awakens unchanged. Nevertheless, generation ships are our bridge until physics yields new possibilities, beyond warp drives or wormholes. They are human-sized answers to cosmic timescales. To cross the gulf between stars, humanity must adapt, endure, persist. The generational void is a river we must learn to navigate, a test of endurance as profound as the distances we face. In this void, we search for meaning, purpose, hope. Each generation born aboard is a flicker of light against the cosmic dark, a candle borne forward into the silence. Some will see new suns, others will only hear their distant echoes, but all will carry humanity's burden and promise, bridging the impossible gulf with unyielding life. Time behaves strangely when you move close to the speed of light. On Earth, a second is a second, but aboard a spacecraft nearing light speed, time stretches and slows. This effect, called time dilation, means travellers can experience months where years pass outside. It sounds like a solution: cross vast distances in a human lifetime by slipping through time itself. But the universe has a catch. While time slows for travellers, it rushes relentlessly elsewhere. Imagine you embark on a voyage to a star 4 light-years away, travelling at 99% of light speed. For you, the journey might take only a few months. Your clocks tick slowly, your aging slows. But back on Earth, 4 full years elapse. When you arrive, the world you left has aged much more than you have. Friends have grown older, cities changed, technologies evolved. You have crossed space in your own frame before the distant star, but you have also crossed rivers of time that divide you from home. This velocity advantage does not erase the problem. The universe ages even if you do not. Decades accumulate on the world you left, centuries on longer voyages. A trip to the galactic core, 26,000 light-years distant, would feel like a handful of years to you travelling near light speed, but 26,000 years in Earth's frame would pass. You would return to a world unrecognisable, perhaps extinct or evolved beyond recognition. Communicating across these relativistic distances carries paradoxes of its own. Messages sent to and from a relativistic traveller suffer delays, distortions, and alignment problems. Signals pile up, arrive in bursts, or vanish into horizons where catching up becomes impossible. For the traveller, Earth may go silent, a ghost of home fading into the cosmic night. The relativity trap underscores a cruel paradox. We can speed up our own clocks as we journey, slipping through time's river faster than those left behind, yet the price is separation. The faster we go, the more locked we become out of synchrony with the universe we left. Lazarus paradoxes and communication blackouts compound the isolation of deep space travellers. The journey feels short, but the void it opens is vast. This paradox shapes every vision of interstellar travel. Time dilation offers no easy passage. It is a double-edged sword. It allows survival across distances far beyond normal lifespans, but it widens the gulf between traveller and home, exacerbating isolation and complicating communication. Travellers become voyagers between different eras, crossing not only space but the relentless flow of time itself. This is the relativity trap, the cosmic price of pushing speed to its limits. It offers escape and exile entwined, speed wrapped in loneliness. Light speed remains too slow, and faster than light remains forbidden. Between these boundaries, humanity must find a way to live, endure, and dream. Between stars lies silence, not just the silence of empty space, but a silence enforced by the immutable speed of the light. Even if we send spacecraft to nearby worlds, communication across these vast gulfs confronts staggering limits. Messages travel no faster than light, meaning round-trip conversations could span decades, centuries, or much longer. Sending a single signal to the nearest star, Proxima Centauri, takes 4.2 years. Waiting for a reply doubles the wait to over 8 years. For stars tens or hundreds of light-years away, the delays multiply. Conversations become slow-motion exchanges, stretched beyond the bounds of human patience. The vast distances turn communication into long echoes that fade before answers arrive. For spacecraft travelling close to light speed, the situation becomes even stranger. Relativistic effects distort signals, causing delays, compression, and horizons beyond which information cannot reach. Messages can be lost in cosmic gaps. Communication networks become one-way corridors or sparse bursts of data delivered only at a journey's end. Engineers and physicists envision solutions using quantum technologies. Quantum entanglement promises instantaneous correlations between particles regardless of distance, but not faster-than-light communication. Experiments in space, like the SEEK quantum entanglement setup on the International Space Station, demonstrate the resilience of entanglement in harsh environments and the possibility of long-distance quantum communication. Yet, fundamental physics forbids using entanglement alone to transmit information faster than light. Practical quantum networks in space rely on delicate exchanges between satellites, ground stations, and quantum memories, overcoming losses and noise across atmospheric and orbital channels. These breakthroughs edge us closer to a quantum internet spanning Earth and eventually beyond. But for interstellar distances, quantum communication faces monumental engineering challenges, from beam divergence over light years to maintaining entanglement fidelity. In the meantime, interstellar travelers, probes or people, will face profound isolation. Autonomous operation becomes essential. Spaceships must house intelligence capable of independent decisions, repairs, adaptations. Messages from Earth may never arrive in time, or at all. The communication abyss is a gulf of silence as wide and deep as the space between stars. This abyss shapes mission design. Probes sent beyond the solar system gather data silently and transmit only after centuries or millennia of travel. Crewed missions must prepare for absolute isolation, psychological fortitude and solitude on a scale humanity has never known. Communication is a precious rarity, not a given. The light speed barrier does more than slow travel. It isolates travelers from their origin. It separates explorers from home not just by space, but by time and silence. In this void, voices fade, messages gather dust, and the universe awaits those brave enough to venture forth into the cosmic abyss. Reaching near light speed is only half the battle. Just as daunting is the challenge of slowing down. Accelerating a spacecraft to a significant fraction of the speed of light requires enormous amounts of energy, but the same is true for deceleration. A ship hurtling through deep space at 20% of light speed cannot simply flip around and brake. There is no air, no friction, no convenient way to slow down except by expending equally vast energy. The energy needed to decelerate a craft from near light speed rivals, or exceeds that required to accelerate it. Without slowing down, any mission becomes a high-speed flyby, skimming past stars and planets at velocities too high for detailed study or safe arrival. Imagine a visitor passing through a city at highway speeds without stopping, only a blur of lights and distant noise. The same would be true for a spacecraft rushing past a distant world. Generation ships travelling at modest fractions of light speed face the same problem, but stretched across centuries or millennia. Slowing the massive vessel without machinery prone to failure becomes a monumental engineering challenge. Propellant to reverse velocity must be carried or created on board, increasing mass and complicating design. Current propulsion concepts such as laser-driven light sails propose decelerating by using stellar winds, magnetic fields, or secondary lasers at destination stars. These ideas remain speculative. Positioning and sustaining a deceleration laser system years or centuries ahead of an arriving spacecraft stretches the bounds of technology and planning. Without a practical solution to deceleration, interstellar travel remains tragically incomplete, an endless race with no safe harbour. Spacecraft might approach new worlds at breathtaking speeds, but the inability to slow down and explore means they remain ghosts, passing through without ever truly arriving. Deceleration is the unseen shadow that trails every interstellar mission concept. It demands energy, innovation, and sometimes sacrifice. It also serves as a reminder that light speed, while a universal limit on velocity, is only part of the story. Mastering the art of slowing down may be the key that turns distant stars from unreachable lights into new homes. The universe holds its secrets behind vast distances and relentless speeds. As humanity stares out into the cosmic ocean, the deceleration problem stands as a final barrier, a slow, inexorable gatekeeper to the realms beyond light speed. If accelerating to a fraction of light speed demands staggering energy, decelerating once more is no less formidable. Rocket fuel and propellant become prisoners of physics, their mass ballooning to impossible proportions when attempting high-speed interstellar travel. The fundamental problem is the rocket equation. To reach greater speeds, you must carry exponentially more fuel, which itself adds weight, requiring even more fuel to accelerate and then slow down. Carrying enough conventional fuel to slow down a spacecraft travelling at near light speed is simply impractical. For every kilogram of payload, tons or thousands of tons of fuel might be required. This creates a paradox. To reach the stars, you first have to carry almost infinite fuel just to stop once you arrive. The spacecraft begins to look less like an explorer and more like a massive fuel tank with a pinhole-sized payload. Innovations propose alternatives. Magnetic sails use large magnetic fields to deflect interstellar hydrogen ions, generating drag to slow a craft without using propellant. Combined with electric sails that capture charged particles to produce thrust or braking force, these concepts offer propellantless deceleration, leveraging interstellar matter itself as a brake. Beamed propulsion presents another possibility. A spacecraft could harness giant laser arrays assembled in the home system to power acceleration. But slowing down might use lasers set up near the destination star to decelerate a light sail by radiation pressure, an idea that demands infrastructure orders of magnitude beyond anything we have today. Gravitational assists, a technique already in use within our solar system, could help. By looping close to massive bodies like stars or black holes, spacecraft can gain or lose velocity through gravity's invisible hands. Concepts imagine using the corona of a star as a frigid brake, skimming through plasma to decelerate with the star's magnetic fields or atmospheres. These maneuvers require exquisitely precise navigation and materials capable of withstanding intense radiation and heat. Emerging ideas explore using interstellar medium interactions, harnessing momentum exchange with charged particles, or even using streams of slower particles, pellets, to transfer energy and slow the spacecraft. While these remain theoretical, they hint at ways to stretch the limits of physics without relying on massive fuel stores. Fuel impossibility is more than an engineering challenge. It is a fundamental barrier imposed by the laws of motion and energy conservation. To turn speedy vessels into explorers prepared to stop and linger, humanity must invent new tricks. As we stare into the void beyond light speed, energy keeps the door locked, and fuel, whether carried or scavenged, may hold the key to finally opening it. This enigma shapes every design, every mission profile, every dream of travelling between worlds. Without solving the fuel problem, reaching distant stars remains a ghost chase, an endless sprint with no safe arrival. The universe is not static. Space itself stretches, carrying galaxies away from each other in an unending expansion that reshapes the cosmic landscape as travellers attempt their journeys. This expansion means that the distance between 2 points is not fixed but grows over time, even as light itself crosses the void. Imagine setting out for a distant star or galaxy. As you accelerate to the limits of light speed, the space between you and your destination expands relentlessly, stretching the gulf across epochs. The farther you travel, the more the universe swells beneath your feet, a cosmic desert that grows wider even as you sprint across it. This expansion enforces a harsh limit. Beyond a certain horizon, galaxies recede faster than light, not because they violate physics, but because space itself expands. This cosmic event horizon means some regions of the universe are forever unreachable. No spacecraft, no matter its speed, can ever catch them. They drift beyond a boundary, their light unable to bridge the gap. Travellers face an expanding archive, a river of space unfolding beneath them and the stars they seek. Even if accelerating to near light speed, the universe ages and stretches on relentlessly. The expansions means that arriving at distant galaxies may require escaping not just space, but expanding space-time itself, a challenge beyond current physics. Observers on Earth measure redshift, galaxies appearing stretched toward the red end of the spectrum, as the signature of this expansion, a siren song of the cosmos receding. This shift tells us how fast galaxies move away and how vast the distances have grown since their light began its journey. The expansion factor shapes every vision of cosmic travel. It demands waiting not only for distances to be conquered, but for the universe itself to cooperate. Some destinations become islands forever out of reach, their light extinguished from our view by cosmic expansion, and their stars forever invisible. This stretching of space is a sobering reminder that the universe is not merely a backdrop to our dreams, but an active participant with rules that direct how far and how fast we may go. Light speed remains a prison wall, while the expansion of space itself stretches the bars further apart. In the cosmic dance between speed, time, and distance, expansion plays its relentless part, tugging galaxies away, widening gulfs, shaping the endless frontier where light speed is fast, but the universe is vast beyond measure. In the vast ocean of the cosmos, we are cast not as explorers voyaging freely, but as islanders trapped within a cosmic archipelago. Our Milky Way, our local group, even our Virgo supercluster, all are islands in an expanding sea of space, and the gaps between them grow relentlessly wider as the universe stretches. We live in a bubble, a local island universe surrounded by boundaries that light itself cannot breach. The expansion of space creates event horizons, boundaries beyond which galaxies recede faster than light. They are forever lost to us. No travellers will ever cross these borders. No signals will ever reach us from beyond. These cosmic islands remain forever isolated. Within this prison of distance and expansion, we peer out with telescopes, mapping galaxies, clusters, superclusters. We see neighbours we cannot visit, systems within reach only of light's long journey, but inviolate to any craft bound by physics. We study these places, but we are detached, touching them, walking their lands, breathing their skies. This may remain forever out of reach. This island universe reality is a cruel paradox. Our desire to explore and extend our presence clashes with the immovable barriers of distance and the speed of light. We may send robotic emissaries propelled by lasers and magnetic sails, but even these are confined to the smallest local islands by energy and time. And what about life beyond these cosmic shores? If the distant galaxies contain civilizations, they too are prisoners of their local bubbles. The vast emptiness is a divider, not a bridge. Isolation at cosmic scale becomes a universal condition. Civilizations locked inside their islands, staring outward but never crossing, speaking across eons to silent voids. To dream beyond this island, to bridge these cosmic gulfs, will require breakthroughs we cannot yet imagine. New physics, new propulsion, new dimensions. Until then, we remain castaways on the shores of our small local universe, gazing at horizons endless yet out of reach. A cosmic archipelago of light and shadow, infinite distance, and eternal longing. When you look at the stars, you see not only distant suns, but echoes from ancient times. The light that reaches us from faraway galaxies has travelled for millions, billions of years. These photons are messengers from the past, carrying stories from epochs long before humanity walked the Earth. The farther the galaxy, the older the light. When we observe a galaxy 10 billion light-years away, we see it not as it is now, but as it was 10 billion years ago, when the universe was less than a quarter of its current age. Those galaxies may have transformed, merged, or vanished since their light began its journey here. The stars we see might be ghostly relics of vanished worlds. This ancient light defines our cosmic horizon. It marks the boundary of what we can know, what we can see, what we can hope to reach. Even at light speed, travelling to those distant galaxies means crossing a gulf measured not only in space but in time. A voyage that might take billions of years would arrive at a destination transformed beyond recognition, if it arrives at all. Sometimes the light is all we have. It is the archive of creation, the fossil record of the cosmos. We read it to understand the universe's birth, evolution, and future. Yet the ancient photons also remind us of the universe's relentless pace. Stars live and die, galaxies collide and merge. The universe ages while travellers cross the void. The paradox deepens. The light we see may belong to stars and galaxies that no longer exist. Their light reaches us as a fading whisper of a vanished past, a chorus from an extinct cosmic era. We are, in that sense, time travellers, witnessing events long ended but preserved by light's persistent journey. As we contemplate travelling to these distant places, we face the challenge of joining that ancient light, the desire to cross eras as much as space. The light speed barrier is not just a limitation on velocity, but a boundary between past and future. It is a river of memories we float upon, a journey through the cosmos's ancient archive. To reach beyond this ancient light, we must dream beyond speed. We must seek new physics, new technologies, and new ways to fold, tunnel, or leap across space and time alike. Until then, the universe's distant past remains forever shut, accessible only to eyes that can see but hands cannot touch. The speed of light does more than set a velocity limit. It guarantees cosmic isolation. Even if we perfect the technology to reach near light speed, the distances are so vast and the timescales so long that travellers become islands of solitude adrift in space and time. Between stars, centuries or millennia may pass during a voyage. Generations born and die aboard ships that drift far from home, cut off by immense voids and the unyielding speed limit of light. Communication, slowed by light speed delays and disrupted by relativistic effects, becomes sparse and fragmented. Messages arrive years too late or not at all. Crews face the abyss of silence, knowing Earth may be a fading memory and any contact may never come again. Even robotic probes, armed with swarms of tiny instruments and laser-driven sails, are alone in the void. They race forward, gathering data that may not reach Earth for decades or centuries, lost in the vast communications gulf. This loneliness is a cosmic equation we cannot escape. Every light year travelled multiplies isolation. Every fraction of light speed gained carries a heavier cost of solitude. Civilizations, if they arise elsewhere, face the same paradox. Vast distances divide hearts and minds, the universe a tapestry of separated islands. Yet loneliness breeds resilience. It fosters imagination, innovation, and the deepest yearnings of a species that refuses to remain still. Our desire to reach beyond, to touch the distant suns, is the spark that drives us forward despite the cosmic silence. The loneliness equation is the price of the cosmos's vastness, of speed's ultimate limit. It reminds us that the universe is both a marvel and a prison, the stage for epic journeys travelled alone, amid the cold and endless dark. The harsh truth that light speed is too slow to practically bridge the cosmos offers a striking perspective on one of the greatest mysteries in science, the Fermi paradox. If the universe teems with life, as many suspect, then where is everyone? Where are the explorers, the colonizers, the civilizations that have conquered the vast distances between stars and galaxies? The answer may lie hidden in the speed of light itself. Light speed, the cosmic speed limit, is also a cage, a velocity so fast by our standards yet so slow on interstellar scales that it traps civilizations within their own local bubbles. No matter how advanced, a species might never send crewed missions or even probes to stars beyond a few dozen light years without investing centuries or millennia into voyage after voyage. Communication and travel lag, time dilation effects, and the energy required to accelerate and decelerate at meaningful speeds mean the universe is a scattered archipelago of isolation. Civilizations may simply never cross paths. They remain confined, islands in a sea of light and darkness, distant and silent against the immensity of space. This might explain the Great Silence, the absence of detectable civilizations or starfaring visitors. They may exist, sparkling in the dark but trapped by physics and distances, unable to reach us or communicate effectively. Our own species' nascent steps toward the stars are bound by these very same laws. Light speed is not just a speed, it is a boundary that shapes cosmic destiny. So the Fermi paradox is not merely about alien absence, but about cosmic scale and fundamental physical limits. It is a question about the machinery of the universe, the relentless tyranny of distance, and the isolation it imposes on all who would dream of stars. Yet within this paradox lies a spark of hope. The search continues, both for signs of others and for new physics that might open shortcuts, new strategies that might bend the cosmic rules. For now, the speed of light remains our slowest prison guard and our fastest messenger. The universe is vast, silent, and waiting. Among the most tantalizing hopes for surpassing the cosmic speed trap lies quantum entanglement, a phenomenon Albert Einstein once called spooky action at a distance. Two particles become linked so that the state of one instantly determines the state of the other, regardless of the distance. Could this be humanity's ticket to instantaneous communication across the stars? Recent advances demonstrate entanglement over tens of kilometers, and in spaceborne experiments verify the stability of entangled states through Earth's atmosphere to satellites. The development of quantum networks, quantum memories, and quantum teleportation protocols could revolutionize communication security and speed within our solar system and potentially beyond. However, current understanding of physics places strict limits on quantum entanglement. It does not allow faster-than-light communication because measuring one particle's state produces random outcomes. A classical channel is still needed to interpret the results, bound by light speed. Any transmission of usable information must obey causality and the universal speed limit. Yet, innovative concepts propose advanced architectures of quantum communication networks stretching across space. These include satellite quantum repeaters, multiplexed entanglement, and fault-tolerant algorithms proposed to maintain entanglement fidelity over vast distances and time. Such quantum-enhanced interplanetary or interstellar communications remain theoretical, but are a focus of cutting-edge research. Could quantum technologies lessen the profound communication delays haunting interstellar travelers? Can entanglement-assisted communication someday support deep space missions, expansions of the interplanetary internet, or even act as the backbone of interstellar cloud computing? These possibilities inspire hope but remain far from practical realization. For now, quantum entanglement symbolizes the vivid dream of transcending light speed's tyranny. It represents the frontier where physics, technology, and imagination intertwine, opening doors to communicate, compute, and perhaps someday voyage across the stars in ways classical theory forbids. It is the ultimate challenge, the cosmic whisper of hope within the unyielding silence of the vast night sky. If light speed is the universal speed limit, how can humans ever hope to travel faster to explore the stars? The answer may lie not in breaking the rules of physics, but in bending the very fabric of space-time itself. In 1994, theoretical physicist Miguel Alcubierre proposed a concept now known as the Alcubierre warp drive, a revolutionary idea based on Einstein's general relativity. The warp drive envisions creating a bubble of space-time around a spacecraft that contracts space in front of it and expands space behind it. Instead of the ship moving within space, the bubble moves through space, enabling apparent faster-than-light travel while locally obeying relativity. Inside this warp bubble, the spacecraft remains at rest relative to its surrounding space-time, avoiding relativistic effects like time dilation. This concept echoes the cosmic expansion of the universe, where space itself stretches faster than light in distant regions, a phenomenon allowed by relativity since it involves moving space, not objects within it. The Alcubierre drive applies this idea on a local scale to enable superluminal travel without violating fundamental physical laws. However, the theory demands exotic matter with negative energy density, something not yet observed or fully understood, to generate the required spacetime distortions. Early calculations suggested the energy demands were astronomical, far beyond current or near-future humanity's capabilities. Later refinements reduced these requirements, but not to practical levels. Modelling also predicts quantum instabilities and issues with energy conditions, raising questions about whether such warp bubbles could be stable or even exist in our universe. The regions near the bubble's boundaries might generate intense radiation or tidal forces harmful to occupants. Research continues to explore alternative geometries and conditions to address these complex challenges. Despite these hurdles, the Alcubierre warp drive remains a compelling framework for imagining faster-than-light travel. It sparks scientific and philosophical dialogues about the limits of physics and human ingenuity. Exploring this idea pushes the boundaries of relativity, quantum theory, and cosmology, suggesting that while light speed remains a hard limit for travel within space, manipulating space itself may one day make the impossible possible. The warp drive is humanity's boldest dream of escape from the cosmic speed trap, an elegant, if speculative, solution that transforms space and time from obstacles into pathways. Whether it becomes reality or remains visionary concept, it captures the infinite optimism of those who dare to reach for the stars. Wormholes, cosmic tunnels through space-time, capture the imagination as possible shortcuts between distant stars or even different times. Emerging from Einstein's theory of general relativity, wormholes theoretically connect two separate points with a bridge far shorter than the vast expanse between them. The dream of wormhole travel promises to sidestep light speed's tyranny, shrinking journeys that would otherwise stretch across millennia into moments. Yet, the physics remain daunting. Most wormhole solutions require exotic matter with negative energy density, a substance not yet found in reality, to stabilize the tunnel and prevent collapse. Without this ghost matter, wormholes pinch shut almost instantly upon any matter entering them, turning cosmic gateways into one-way traps or black holes. Recent models show that even if unstable, a fast-moving probe might send signals back through a collapsing wormhole before final closure, offering tiny slivers of usable communication. As fascinating as wormholes are, constructing or finding one large enough and stable enough for human travel remains firmly theoretical. Research explores alternative geometries, quantum effects, and extensions beyond classical general relativity that might allow traversable safe wormholes. Some studies suggest forms of quantum or modified gravity might permit humanly traversable wormholes without exotic matter, though these remain speculative. Travelling through a wormhole also entails unknown hazards, intense gravitational gradients, tidal forces, and unpredictable space-time distortions that could warp time, space, and the traveller's body or consciousness. Navigation becomes a challenge through enigmatic corridors of the cosmos, where space and time twist beyond everyday experience. Until humanity develops revolutionary technologies and physics, wormholes remain beautiful theoretical passageways and science fiction staples, signs of what might be possible in universes yet to be understood. They are the greatest possible escape from a universe where light speed is slowest, offering the hope to one day bridge the impossible gulf between stars. The challenges of interstellar travel are immense, but so is human imagination. As science advances, quantum entanglement offers a compelling glimpse of the future, promising breakthroughs that could reshape communication and computation across the cosmos. Space-based quantum experiments like SEEK have proven the resilience of entanglement under harsh orbital conditions, paving the way for future quantum networks that extend beyond Earth's atmosphere. The dream of secure, efficient quantum cloud computing and instantaneous quantum correlations across vast distances fuels cutting-edge research. Yet entanglement, for all its wonder, does not violate the cosmic speed limit. It cannot be used for faster-than-light information transfer but could revolutionize deep space communication by enhancing security, reliability, and processing power. At the intersection of quantum mechanics and cosmology, fresh theories explore ways to merge these domains for efficient, scalable space communication and computation. Quantum memories, entanglement distribution strategies, and space-based quantum repeaters are no longer science fiction, but emerging realities that may one day support interstellar missions. The final frontier extends beyond technological upgrade. It demands rewriting the laws of motion, energy, and information. From warp drives to wormholes, from quantum entanglement to novel space-time engineering, the path ahead is uncertain yet filled with extraordinary promise. As the cosmos beckons, humanity stands on a precipice, limited by light speed but inspired by hope, constrained by physics but driven by curiosity, tethered to Earth but yearning to explore. The slowest speed in the universe is still the fastest we know, yet in the depths of that constraint lies the spark that ignites our unending quest among the stars. This is the future frontier, the quest to transcend, connect, and discover in a universe too vast and too slow to traverse at speed. It is the story of light, space, time, and the indomitable spirit of humanity's reach for the heavens.